Okay, hi everybody. I think I'm cooking now. Today we're talking about chapter 4, the physical transformations of pure substances. Essentially, we're going to look at phase changes, solid to liquid, liquid to gas. And the reason is that these are the simplest example of a chemical equilibrium that we can define. My daughter just walked in.
Hello.
All right, phase changes. Very simple and will allow us to develop some tools related to equilibrium. There are two main questions that I want to answer in this chapter. The first is what thermodynamic criteria describes equilibrium, and how does equilibrium respond to changes in pressure and temperature? Before I get into that, I thought it would be useful just to take a second though and define equilibrium itself. So equilibrium is the state in which a closed system exhibits infinitely slow macroscopic changes. That is none. That's my definition. It's not a formal one. And the formal definition to keep in mind, the mathematical definition, which we saw previously in our discussion of free energies, is that equilibrium is when a system is done evolving, right? When it no longer undergoes spontaneous changes. That occurs to the condition in which G is a minimum and delta G equals 0. That is how we define equilibrium. Now I want to make some comments here about this first definition. Why don't I say it's a state in which a system exhibits no changes? Right? What's the importance of a closed system? Well, imagine you had a cup of water out on the countertop. If you walked away and came back a week later, all of the liquid would be evaporated out of the cup. Right? And the idea is that open systems can lose mass. An open system will never achieve equilibrium. It's only a closed system which is contained that can achieve equilibrium. The second, and this is probably more important, is that equilibrium is not a statement that nothing's going on. Right? Equilibrium is in fact a really dynamic process, and I hope that this is sort of known to you. I'm going to give you one quick example. Switch my pen color. Here's my cup. It's now closed. I got water down here, H2O liquid. Up here I have some steam. This is H2O gas. I'm imagining that this is all at 100 degrees Celsius. And if this is true, what's actually happening here is that water is continuously evaporating and forming steam, and the steam is continually condensing and forming liquid water. Right? There's always these changes that are going on, but they're microscopic and they're balanced. Right? There are no more macroscopic changes that are occurring. There's no net change in any of these things, but there's all sorts of microscopic changes that are going on. The other thing to keep in mind is that equilibrium is not ever a statement about rates. Right? So equilibrium, to say that a state is at thermodynamic minimum, right, says nothing about the rate at which we achieve that state. Here's the most famous example. Carbon exists in two solid forms, graphite and diamond. You may or may not know, but graphite is the most stable. That means that all of the diamond in the world is spontaneously transforming into graphite. And this might be bad if you were buying an engagement ring or something like that. But there's a catch, right? And the catch is that process by which diamond transforms into graphite takes millions of years. Right? So we can say a diamond is forever, not thermodynamically true, but if it takes it 1,000,000 years to get there, then who really cares? All right, I'm ready to move on and start answering those questions that I posed at the beginning. But before I do that, I want to just give you a brief interlude about phase diagrams. And I'm not going to belabor this point because I hope that it's all familiar to you. But I do want to point out a couple things. So a phase diagram is a map which shows which phase is most stable at a particular temperature and pressure. It typically looks something like this. Pressure on the y-axis, temperature on the x-axis, and they have this, usually a Y-type shape. At low temperatures and high pressures, solids are most stable. At high temperatures and low pressure, gases are most stable. And in between, we get liquids. You can read off a couple important points on here. One is really 1 ATM. So if I were to go across here at 1 ATM, I would see the point where the solid and liquid areas intersect. And that's the melting temperature, the melting point, the normal melting point, right? So the fusion temperature, where the liquid and gas intersect, is the vapor, the boiling point, right? TVAP, vaporization. I can read those things off. This also suggests an important note, right? Which is that in the areas of this graph, one phase is most stable. It jumped on me again. But on the lines, two phases coexist. So if this is the normal boiling point, right, I can have a liquid and gas in equilibrium. And that's true any place along this line. Right? Here I have the solid and liquid in equilibrium. Both of them can exist. And there's this one important point on here, which is right here. And if you look at this, you'll see all three come together. It's called the triple point. Three phases. There's generally speaking one set of conditions in which three phases can exist at one time. So it's important for calibration and things like that. Wanted to give you a couple of quick examples, specific examples. So this one is carbon dioxide. It's a prototypical substance. You can see this sort of Y-shaped kind of thing. Here's 1 ATM. Right? If I look across this, what I can see is that the solid and gas are in equilibrium. Right? So CO2 sublimes, goes right from a solid to a gas. Right, look out at 1 ATM and room temperature, you see that the gas is most stable, so this all jives with our experience, and all of this makes some sense. Here's a little different one. It's water. So here's a phase diagram for water, and water's a little abnormal, right? Specifically, you can see that the Y is differently shaped. Right? That is that this line between the ice and water phases goes backwards, has a negative slope. And this is a really interesting phenomena that I'll talk about a little bit later. If you zoom out a little bit more, right? So here I went up to like 200 ATM. Here I'm up at 10 to the 9th Pascal, right? So it's a much broader dynamic range. This is what the full phase diagram of ice looks like. And I point this out to you for sort of one funny reason. All of these ones that are labeled by Roman numerals are phases of ice. Ice is actually a really highly studied subject, how it forms, why it forms, all these different phases. And they're labeled. So this is ice 1, ice 2, ice 3. You can go through and look at all of these, and what you'll start to recognize is that some of them are missing. And the most famous one that's missing is ice 9. Right? So I don't know if any of you are Kurt Vonnegut's fans. If you are, you may have read this book, Cat's Cradle. It's about a crazy scientist who discovers ice 9 and threatens to throw it into the oceans and crystallize the oceans. It's a really interesting read. So if you got some spare time, maybe you check that one out. All right, I think I'm going to stop here. Yep. And I will post this video. We'll talk next time about thermodynamic criteria to establish equilibrium, and I will see you then.